So with that, take it away, George.
Yeah, thank you, Carl, for the introduction. I didn't realize you were going to read the whole bio. So, hello, everybody. Thank you for attending this talk. I'm Georgios, and I'm going to talk about our cross-modal map learning for vision and language navigation. This is the part of our work in navigation which focuses on incorporating instructions in navigation tasks. And so there is a clear high-level objective here when it comes to incorporating language, and that is that most robots nowadays require some expertise to operate, and you need some trained user to interact with the robot. And so this is a major hurdle when it comes to having robots in every house, right? The communication aspect and the interaction. And the objective is to essentially enable these robots to operate in everyday environments with people that don't have formal robotics training. And the most natural way of interacting with robots for us is using language, right? So there are very simple and use cases that you can imagine. So, for example, you can tell your Roomba to go and clean under the table at a very specific location. You don't need to kind of try and find the software and click on the particular part of the map or whatever. Or, for example, if you have some robotic manipulator helping you during cooking, you can give, for example, specific instructions on how to kind of move stuff or prepare things. Now, we study this problem in the context of vision and language navigation. I will be referring to this mostly as VLN. And so here, for this problem, we are given a human-generated instruction in natural language. And we need the agent to make appropriate actions, to decide on appropriate actions in order to follow the path that the instruction specifies. And here, the agent, at least the way this task is defined, you do not have access to the map. A lot of the times, this is we also evaluate in novel environments, which the agent has not seen before at all, not even trained on. And the idea here is to plan the path that corresponds to the instruction that we have. Also, notice that we don't know where the goal is exactly. And the goal is implicitly defined by the instruction itself. So there are a lot of challenges for this program. So first of all, the first challenge comes from the language side. So language is very diverse. There are a lot of different ways you can actually describe the same path that can come from multiple human subjects. And also, the instruction itself can be ambiguous. So it says here, you're in a bedroom, turn around to the left until you see a door. There might be two doors in the bedroom, right? You don't know exactly which one you're going to follow. Another major challenge is the environment itself. You have partial observability, right? You don't really see the entire space. You don't have access to the map. You only rely on a very narrow field of view in order to understand where to go and where to move next. Also, the environments themselves are realistic and unstructured. We operate in the real environments here. I'm going to show more about the data set later. And also, there are challenges when it comes to identifying the goal. The goal is implicit. You need to understand where the goal is to make the decision to stop. Right, so that's also a challenge. And another thing that is a lot of the times overlooked is the fact that while you're executing the instruction, you need to be able to understand which part of the instruction you've actually executed and finished, and which part of the instruction you need to start looking for next. Right, and this is actually very, very difficult to do. Now, arguably, the biggest challenge here is actually the grounding of the natural language on the visual input. And by grounding, what we mean is the association between the words in the instruction and features, for example, in the visual input. And those could be associations at the spatial level, meaning how far things are, or on the semantic level, meaning associating certain words to certain parts of the image that belong to certain objects, or even the actions like turn left and right, move forward, and so forth. And these are some of the scenes that we've been using. I just wanted to give a few examples here. On the left, these are the observations that the agent can get from the environment, and on the right, these are bird-eye view images of the environments, with the bottom two being the semantic representations of those environments. Each color corresponds to a different semantic label that could be, you know, couch, free space, chair, and so forth. And so a lot of the current literature mainly tries to address this problem by trying to learn this association between the language with the images, either using some unstructured implicit representations like Georgios, LSTM, RNNs, or they try to use some attention mechanisms. So there are two main problems with this. The first problem is that all of these methods try to learn this association directly on the egocentric view of an agent, the observations perfectly. And the other thing is that most of these methods are actually end-to-end, meaning that they will have the RGB and the depth and the instruction as an input, as the state of the system, if you like. And then they have some implicit unstructured way to kind of keep track of that state and try to predict actions end-to-end. So one of the main problems with this type of approach is that these methods essentially require to implicitly learn all different modules of a navigation system, meaning mapping, planning, and controller. And they have to do it directly from the images. So they go directly from images to actions. Now, this is actually in contrast to what we know or what we've researched about how biological systems actually solve navigation. And we have a lot of evidence to suggest that biological systems like rats, for example, built map-like representations of the environment. And there's this very famous experiment by Tolman way back in 1948, where he would put rats into this map here on the left. So he would put these rats into this circular area, and there was some sort of reward at the end of that corridor on the right, maybe some food or something. And then the rat would always try to kind of follow this corridor and then go to the reward. And then he would take the same rats and put them in the maze to the right. And he would notice that the rats would always try to go in the direction of the food, meaning that the rats would actually try and use a shortcut to actually get to the goal. And most of the time, they will even try to go straight. Essentially, this suggests that rats would actually build this cognitive match that allowed them to understand where the goal is with respect to their self and take shortcuts. Now, more recently, there's been a lot of studies regarding the usage of landmarks and semantics and how we humans actually build these spatial representations using landmarks. And so this particular study, they tried to evaluate how good of spatial representations we build when we are actually given landmarks into the instructions versus not given landmarks into the instructions. So human subjects, for example, they were given like a sequence of images here to the right, where that was accompanied with navigation instructions. And in one case, they were given navigation instructions that included specific landmarks, like, for example, this is that's the public restroom, and then to your left, there's a shop or something, versus given instructions where they were just given specific path to follow, meaning move forward, 5 meters, turn left, and so on. And so they found out that humans could actually recall the paths weeks after this experiment, much better if the instructions included landmarks. So this essentially suggests that we generally anchor these landmarks and semantics in some map-like representations that we build. And so, inspired by these recent and older studies, what we're doing here is that we are actually proposing a fundamentally different method to address the VLN problem. And we do that by grounding the language actually on spatial semantic representations, rather than doing it, first of all, rather than doing it end-to-end, and also rather than grounding these representations on the egocentric observations, right? And we do this with two steps. Given an RGB-D image and the instruction, we first predict an egocentric map, and then we use that egocentric map to predict a path. Now, I'm going to go into a lot more detail about exactly how this happens later, but before I even start talking in details exactly how we do this, I want to take a step back and discuss a bit some initial experiments we did on this problem. Now, first, we actually wanted to investigate whether our assumption of using the semantic maps was actually valid. So we reformulated the problem and we said, okay, if vision here is solved, right, meaning that we have access to the global or allocentric ground truth map, can we actually learn to predict the path given the instruction, right? And here we wanted to investigate actually, can we find these associations between the map and the instruction? And here on the right, you can actually see the path that is predicted. The blue dots here are is the ground truth path that the instruction defines, and the red dot are our predictions. So this is just an example of the task that we actually formulated here and we tried to solve. And the main idea was to find these associations between the instruction and the map. And so, for example, I've highlighted a few cases here. So if you see, if we see the blue highlighted text here that says take the opening, this one here corresponds to that part of the map, which is an opening, it's basically a door that the agent has to go through. And the idea is, can we actually learn some feature representation that can give us this association? Notice that something that is interesting here, for that particular part of the map, the instruction says take the opening, which is really not a very common way to say, like, go through a door, right? You can actually say this in all different ways, but we still need to be able to actually associate that part to the instruction, right? And there are a lot more examples that I could talk about here, but let's go into a bit more detail about the model itself. Now, given the global map and the instruction, what we have first is we have some, first for the map, we have like an encoder to give us a certain encoding for the region of the map. And then we also have the BERT model, which is very well known in NLP, to give us some representation of the word. And then what we do is we actually use a cross-modal attention architecture to learn this attention matrix here. And this attention matrix, what it is basically, it's just the learned similarity between each word in the instruction and the map region that we have, right? And this is exactly as this is from the attention result unique paper from NLP. People that are familiar with NLP are very well versed to it. I'm not going to go into a lot of detail about how it's defined, but the main thing to remember is that it learns this similarity between two modalities, right? And the actual output here is this decoder on the right, which is a representation over the map that we learn. And then that representation goes into an encoder-decoder model that predicts the path. Okay, we don't really need to go into too much detail about this, The important part here is to remember that whatever representation comes out of the attention module goes into the waypoint prediction model, right? And we predict the path as a sequence of waypoints, okay? So this is one qualitative example I wanted to show. So here I highlighted a part of the instruction for which I also put a blue rectangle there. So here the instruction was saying walk through the doorway to the right of the towels. Once you're through the doorway, take the left and head towards the gray couch and ottoman. And we can see that the model is actually predicting waypoints that reflect that. In this case here, you can see the couch being this cyan color here, and also the ottoman here is this purple color, and this is the table that is being referred to as well. So this essentially is basically just the first few waypoints in the instruction. So this was actually a good prediction. But what we're mostly interested in was actually in seeing that through this waypoint prediction path, can we actually learn the similarity between the two modalities? And we dissected the attention matrix A, and we visualized the attention features for a specific word in an instruction. And what we noticed was that the attention matrix learns to put more weight on areas that correspond to that semantic object. And here you can see, so you can see here that a lot of the most bright areas here correspond to higher activations of this attention. And so you can see that most of the times the attention is over some open spaces where you can actually walk through, and a lot of the times it's actually directly on the doors itself. So we were encouraged by these results. And so we then moved on to solve a simplified version of the vision and language navigation task. By using, instead of the global map, we were actually using the ground truth egocentric map. So this is the ground truth egocentric map that you see over there. And by egocentric map here, it means that the agent is in the middle of the map and looking forward. Okay? And now we are actually also using the cross-modal path attention as before. This is the same attention module as we had earlier. And something I want to emphasize here is that this attention module defines an input to be a query and one input to be a key here. And in this case, we use the map, the egocentric map, to be the query and the instruction to be the key. The idea for this is that because the map now here is egocentric, while the agent is moving, the map is changing, right? And the instruction stays the same. So you always use the same instruction for the entire episode. And so you can think of this conceptually as being the map querying the instruction for the path. So that last part of the model is the waypoint prediction part, which is going to give us this sequence here of the waypoints that I was mentioning. And in this case, the waypoints are in the egocentric frame, right? They're always with respect to the agent. So please interrupt me if you have any questions. Yes.
I have one. When you said same module made was trained on the full map, right? It's not. Are you training the cross-modal attention again now?
Yes, yes.
Okay, so it wasn't initialized by being trained on the full map.
No, it wasn't.
Okay.
It wasn't because here you want this model to actually learn to change the representation depending on the observation of the agent, right? And the orientation of the agent. Because go ahead.
It wouldn't help to initialize it by learning some like mapping. So that I don't know how they represent like the egocentric view versus the full map view, but it wouldn't help learn attention from a full map and then initialize it there and then get the learning from
maybe it would help a bit, but I'm not. I think because this is fundamentally different in terms of the representation that it has to learn to account for the motion of the agent.
Okay.
Because in the previous case, when you have the global map, you don't have any motion. The map is always the same.
Yeah.
Here, you're only looking at a glimpse of the environment. You're just cropping, imagine you're cropping a small part of the global map, depending on what the orientation and the poses of the agent. And you're passing that into the cross-modal attention. So it's the same architecture, but it's trained again.
And yeah, okay, from scratch. Okay. Thank you so much.
Yeah, sure. And actually, so now that this is trained again on the egocentric maps, we wanted to, okay, that's the loss function we use. I'm not going to go into the detail. So we wanted to dissect again that attention in the egocentric case now. So we saw an example on the global map. Now we can see one example on the egocentric case, and you can see those on the right. So the top example, we took the attention activations for the word couches, and we see a lot of overlap between the couches that we see in the semantic map. So this is the cyan color here corresponds to couches. And we see the same thing here corresponding to tables. We have a lot of examples here in our supplementary material. But the important part here is that this similarity, this attention matrix, is actually learning this correspondence between semantic regions in the map and tokens in the extraction. Now, one important aspect that I want to highlight here is that after looking at a lot of these examples, we notice that the attention actually lights up when the particular object is relevant to the path itself. So if a certain object on the map here is not really part of the path, doesn't really matter whether you actually reach the target, the attention doesn't really learn the association. And that makes sense, right? This is trained to predict the path. Now, similarly, we also visualize the representation of the output of the attention, not just the similarity matrix. And this essentially comes down to a representation over all the map regions. And what we notice is that it tends to learn a feature representation that corresponds to the goal that we're expected to reach and some part of the path. So this is actually a representation that goes into the waypoint prediction module. So this was also very encouraging. Now, okay. Now, up to now, I've been using only ground truth semantic maps. We started with the global map, we went to the egocentric map, but the actual VLN task uses the egocentric observation, right? The RGB-D. So all these experiments we did earlier, they were nice and good, but they're not solving the problem. However, we need to consider one more issue here. Now imagine, take this case here. We have an instruction that says exit bedroom into hallway. And the only thing that you're looking at is actually this bed. You have no idea where the door is. So the door could be maybe on the left, maybe on the right. And based on just this observation, you need to actually estimate the path. You need to actually predict, will I go to the left or will I go to the right? And so this implicitly means that you require, right, to predict unobserved semantic information about the scene here. You need to be able to infer what is the most probable location for the door to exit the bedroom, if it's on the left or the right. And you need to be able to actually take into account this, the semantic structure, the semantic layout in the scenes. And so we've actually design the system, and this is part of our previous work with Bernadette and Carl, that we are actually doing this map prediction over unobserved areas. And so given an RGB-D observation, first we were predicting the semantic segmentation of that RGB observation. We were ground projecting that. And then we were also ground projecting the depth, and then predicting the occupancy, the unobserved occupancy around the agent. And then we will combine the two and actually predict in the final section to the right, we predict the semantics, the unobserved semantics of the scene. So without going into too many details about this, the main objective here was to learn these associations between semantic objects, right? For example, if you're looking part of the table, then there's probably going to be chairs around, right, in the unobserved space. Or if you're looking at a couch, then there's probably a coffee table in front of it. Even if you're not observing the coffee table, you know that there's a very high probability that there is a coffee table there. Right? So we wanted to capture that into our model. And generally, it seemed to be working very well. Now, how is this actually incorporated into the VLN? Yeah, this is how we train it. So how is this incorporated into the VLN? So this is the map prediction part of the model that I just incorporated. And notice here that since we also have the language, and the language also provides some extra information here, we can actually pass the language itself into the map prediction model to learn, again, the associations from the language to predict this semantic layouts. And this is, again, incorporated using another cross-modal attention model that learned the association between the incomplete maps and the instructions in order to predict the map. And then for the final stage, we just incorporate the path prediction that we had from before. So earlier, what I was essentially talking about was this part of the model, which is just the path attention. And then here we used to have the ground truth maps. Remember the egocentric. Now we are also predicting them. So this model essentially addresses, well, tries to address the vision and language navigation where you're given RGB-D observations and instruction, and you need to predict the path and go to the goal. Okay, so now the first thing that we tried was we actually wanted to see how well the map attention itself, meaning how well this particular model here helps when predicting the maps and the path. Meaning like when we incorporate the language into the map prediction, does it actually help? And the answer is yes. Here we see an increase both in the semantic segmentation part and the prediction of the path. And there's also some nice qualitative examples here where we can see that here on the left, it's the map prediction without the incorporating the language. And in the middle, this is with incorporating the language. We can see that the prediction when the language is taken into account is usually much more richer and diverse. And this is sort of expected for our model because we've already seen that the model already learns to associate words in the instruction to semantic objects in the scene. So this definitely helps in the for the whole task. Okay, and the controller that we employ is something very simple. So given the path that we predict, we will select a certain waypoint to be like a short-term goal during the execution. And then for the action prediction, we use off-the-shelf model to just give us the next action based on the short-term goal that we want to go to. So we just have like a simple way of basically following this path that is being predicted to reach the goal. Okay, and these are our main results. This is on the VLN continuous environments dataset. So the bottom entry here on the table, this is our result when we're actually using the ground truth egocentric maps. And this one here is the full model that we're using with the map prediction. Now here, the most important metrics here is the success rate and the SPL, which is success weighted by path length. So success rate here corresponds to how many times you've actually reached the target. And the SPL takes into account also how long your path was to actually get there. Now, notice that a lot of these methods have make different assumptions of the definition of the problem. So a lot of them either use, for example, panoramic images, or they have some prior scene exploration component that allows them to have a map of the environment beforehand. So we don't make any of those assumptions. We use like the very default version of the task. And I think that the most relevant methods that we compare to are these three. And we generally have very comparable results. And we use a lot less data. So a lot of these methods, especially the WPN-DD that we have there, use like an insane amount of data. I think that one uses like 250 million frames of observation, frames of experience to train. We use around 700,000. So that's like a huge difference in terms of training data. And we can show that essentially by learning the association on the spatial maps and following the map prediction and the path prediction that we proposed, we can actually solve this problem with much, much, much less data.
If
Yes.
you add more data, does the performance improve or does it plateau to that amount of data?
That is a very good question. We don't know yet.
Okay.
we don't know exactly what the ceiling is of this method. We want to believe that having a lot more data from a lot more scenes is actually going to give a more robust model, but we haven't been able to try that. Also note that there is some mismatch in terms of resources that you have, like training this method training on 250 million frames. They were using something like 60 GPUs or something, which we cannot do that. Right?
I was going to ask, is that are those all done by companies as opposed to academia?
So the CMTP methods, the ones with the 12 reference, they are from Stanford, and the rest of them are from Facebook. So yeah.
This is what we found with the other problem too. When we
Yeah.
used all the OS data, it was all companies, so it's like it's hard to test, right? Like to scale to what they use to make the comparison, because it's just not feasible to use that much compute.
Okay, and this is one correlative result. This is one example where the agent is successful. And here, let me just stop this for a moment. So here on the left, this is the RGB and depth observation. On the middle top, this is our predicted map and the predicted path, the red dots here. On the right is the ground truth path, both ground truth map and path. This is the instruction, and those are just the labels of the semantic labels that we have. And so here the agent successfully navigates towards the goal. And we have one more, I think, example here. This is the one, the kid with the bedroom that I mentioned earlier.
So I have another question. So, but essentially, the RGB images, you're only using them to reconstruct the map and the map of the unseen environment, right? And then you forget about them and put that into your.
Yes. Yeah. I mean, most methods, what they actually do is that they just learn some feature embedding from the images itself, and then they just directly kind of use the language with that feature embedding to predict the next action. we have this intermediate step where we actually learn to predict the map itself and actually embed this semantic context, if you like, on like the bird eye.
So that's my question. I'm gonna follow that. Essentially, in their test and scene environment, they have items that do not exist in the training and validation. So how would that generalize to words that you've not seen before? Like, so for example, if there's like you have hieroglyphics in the test set and you haven't seen it in the train set, does it transfer?
What do you mean by hieroglyph? You mean the
like,
language?
So in the test set of room to room, for example, they have items like in the same room we have bathtub, shower, and stuff that have not been seen in the training environment. Does this method generalize to items that have not been seen in the training environment?
So you mean instances or categories? Like if
items, yeah. So it could be like so let's say you've never seen like an abstract painting or in the training set. But there is an instruction in the test set that says, when you see the abstract painting, turn left.
Right.
How does it generalize?
So if it's a category that you have not seen before at all, it won't really generalize. Like it doesn't, it's never trained to predict that kind of label. Now, when it comes to instances, it really depends how different the instances themselves are. However, what we've noticed is that the model generally learns to predict certain semantic labels close to each other. So in the case of table and chairs, for example, if even if the type of the table, the type of the chair is something different that we have not seen before, if the model actually predicts at least one of the two correctly, then it has higher bias to predict the right label for its correct for the coherence based on the coherence of the objects, right? Yeah. So that is something that definitely helps.
You
Yes.
just mentioned instances. What do you specifically mean by instances?
By instances, I mean like chair 1, chair 2, chair 3, maybe some type of chair that you have not seen in the training scenes, but it's visible in the testing scenes, which is actually a very frequent case.
So same categories, but like not the exact same object.
Right.
Can I
Okay.
ask something?
Yes.
I'm sorry.
Yeah. Go ahead.
It looks like you've been working with really dense environments, so the agent gets to see like many semantics probably at, like while it's navigating. The question I have is like, what do you predict when you just see a door? And I would suspect that you would predict the corridor, but if you want to reach the bed and you only get to see the bedroom and you only get to see a door, how do you handle situations like that where you don't have a lot of things to see and decide to go towards the right of the corridor, probably that it gets predicted or left?
Right. So this is learning these associations between objects is very difficult to do when the objects themselves are far away from each other inside the room. So we do notice that the model generally learns these associations when there are like objects that are adjacent, for example, or there are objects that are close by. So here you can see that it already observed this the bed here, so that's already on the map. But notice that here it also predicts a chair. So it kind of the model learns that if there's a bed here, and maybe there's some kind of cabinets here or whatever, then it's very highly likely that there's going to might be a chair or a table somewhere in the same room, right? So it doesn't really always do a very good job in predicting like very far away. So for example, here you can see that there's another bedroom here on this side, but the model is not able to actually predict that, oh, there's another bedroom. Then we have seen cases where the agent is standing like next to a door, and then it's actually able to predict that there's probably a bed inside. But it doesn't necessarily do that very far away. Also, one other thing that we noticed is that a lot of the times it actually predicts that if it sees a bed and it's in a bedroom, it actually predicts a bathroom as well, like maybe next to it, or within the same room, it might predict, toilet or a shower or something. So I don't have examples directly here. We have actually more examples in the other paper. We've been working on. But yeah, that is a very valid question, right?
So you get to keep them up. I didn't realize that you remember what you've seen, like that you have a buffer probably where you store the map, like what you've already seen.
So interestingly enough, the buffer is only on the occupancy. So the model actually is able to predict this every time only by storing the occupancy label, not the semantic labels. So this part here is actually predicted every time. Right, and if you keep going, like it predicts that there is some sort of a corridor there. And oops, I think if you notice, so here, for example, I think this is the label for a shower. So this predicts the shower even before it even observes that there's a shower here. And I think this comes mainly because it predicts a sink and a counter. And it also says in the instruction that there's a bathroom. Right. So the model tends to actually predict a shower, even if in the ground truth, there's no shower here. It's actually a bathtub. Right. So I think it fixes that later. Maybe not.
What are the most common failure cases? Like, have you found any failure cases of this model that are consistent, like patterns in the other analysis?
So the model is still not very robust to go back to the previous example. To a lot of orientation changes. Oops. Sorry about that. So you will notice that, okay, I don't know what. So you notice that a lot of the times the prediction changes based on the orientation, like it keeps kind of moving left and right, and then the prediction kind of is not very good. So there is no really a temporal alignment here between. So that is definitely like a failure case when things change a lot. When you actually move left to right, then the model is not that good. Also another failure case is when you're like in a very small room. Like if you start from a bathroom, then because of ground projection, if you have like very close depth values, then the ground projection is not good and the prediction might not be good. So that's also like another problematic case. I think also another problem is when it comes to small objects. So because this is effectively, this is a semantic segmentation problem, right? This is how we treat this. And objects that are very small and don't have a lot of examples in the training set, it's much harder to predict. So like objects like cushions, for example, even though actually I think here we are successful in predicting some cushions. These are like basically it's this color over there, like over on the sofa, but generally it's very hard to actually learn to predict that. Smaller objects also like plants that might be on tables sometimes, those are also difficult to predict.
I have one last question.
Sure.
So for the language part, do you pass in the entire command in the further embedding, or do you split
Yes.
it up? The entire
Yes. So actually, thank you. I forgot to talk about that. So if you guys remember, I mentioned in the very beginning that one of the challenges is actually keeping track of which part of the instruction you actually cover. Now, we kind of circumvent this problem by passing in the entire instruction at every time step, and then relying on the attention module to learn which parts of the instruction to attend to at every given time. And also we predict the entire path. If you notice, even if we're kind of midway, we also predict the entire path from the beginning to cover for the case that we're using the entire instruction. Okay, so finally, I just want to thank my collaborators on this. So Carl, Karan, Soham, Eleni, Dan, and Kostas actively worked on this VLN project. Bernadette, Anton, and Siddharth were very much involved into other navigation papers, especially for the learning to map thing, the map predictor stuff that I presented. And I want to thank you everyone for your attention. So I'm open to any more questions. Are there any questions from the chat?
There are not any questions in the chat. Anybody who's remote, feel free to unmute yourself and ask a question if you have any.
I had a question about the Oracle success metric. What was that? The Oracle success.
The Oracle success is if you don't need to stop to be successful. So part of the task is that.
What's like Oracle stop? Like an Oracle for making the stop.
Yeah.
Oh. Okay.
Yeah. Basically, the environment tells you that you've reached the target and you can't stop.
Oh.
Yes. Otherwise, you have to actually predict to stop to be within the goal radius to be correct, which is also a major source of failures, right? As you very well know.
Yeah. It's interesting they report it like because did all those other papers report it as like one of the standard metrics?
Yeah.
Yeah, that's interesting because they don't for the other problems. No, it's just a semantic navigation problem.
Yeah, for this they actually report also trajectory length, navigation. There's a lot that I think 3 or 4 more metrics that they just narrowed it down to the more important ones.
Yeah.
And it's interesting to see that this method here actually achieves much higher Oracle success than the others. And the reason for this is because this method has a prior exploration. So they already built the map. So it's much easier for them to actually reach, like pass through the target when they already know the map.
But that's not like the official definition of the task, right? So,
Yeah, that's why, I mean, all of these comparisons, there's an asterisk next to a lot of them because of these different definitions of the task.
Yeah, the panoramic images, is that like actually violating the task definition?
So the default definition is that you use only like 90-degree the field of view. That depends on who controls the definition of the task.
Right. Because I mean, when we've talked about it, it seems reasonable to, if you had an actual robot, to have panoramic view.
Yeah. I'm not arguing against that.
Do you think the panoramas could help with that turning problem that you talked about being a failure case?
I think they could. I think they could because there's a lot less strain on the map predictor to actually learn how to predict, let's say, behind the agent, which is very difficult to do. So I think if you have the panoramas, then it might also help with the path prediction itself. Yes.
Have you played at all with the brightness of the camera? Like if you are in a darker room and you don't get to see very well the semantics probably of the map? Have you tried testing that?
So these scenes here, so they are actually, where's that slide? So these are reconstructions of real houses that I think were performed in the day. And then the simulator was built on top of these reconstructions. And so there is no notion of like illumination here. Like, I don't think you can even play with that in the hard-to simulate. So everything is kind of illuminated the same. Yeah, everywhere. Yes.
So I have a question about the transfer method. that you use.
Yes.
So for that, I guess we're using that to gain a similarity between the tokens in the sentence and the ground truth map, right?
Yes.
And so like my question is that, so when we are trying to like compute for the similarity, do we take into account of the previous, like the waypoints that we have already evaluated?
No.
So
We-
just, no, okay. So we're,
Go ahead.
yeah, so we're just computing similarity on the single time step rather than.
Yes. So at least the way the model that I presented right now doesn't have any temporal aspect
Mm.
to it. So it doesn't use information from different time steps to actually predict the path again. That is definitely something that could help with being more consistent, when you're predicting the path between time steps. The only thing that we actually keep between time steps is we just register the occupancy.
Uh-huh.
So we just have a global occupancy map where we keep updating, but that's just it.
Okay.
Yeah, but definitely the using some temporal component is definitely going to help you. Sure, go ahead.
Okay, so this relies very much on the fact that we're trying to reconstruct pretty much the room and the adjacent areas from the first person view, right?
Yes.
In the map. Do you think the same task could transfer into like data sets that do similar things, but for urban environments that are more unpredictable and not structured rooms, can be more open space? Or do you think that's not somewhere where this modular approach would be applied?
I think it can. I mean, you have to retrain it
On the, yeah, of course, that,
a particular
but-
data set, but so it really depends, how much clutter you have in certain environments, how much support you have for certain labels. But I think fundamentally it's the same. Now, if you have, let's say, an intersection, right, on a road, and you want to be able to detect, let's say, 100 pedestrians that might be in the 4 different intersections, that might be difficult. And also, it might also be difficult for the model to predict the movement. These are static scenes, right?
Yeah.
Nothing moves here. So you definitely need to account for the dynamical environment in case you want to do this, let's say, outside on the street where cars move quickly, pedestrians, cyclists, and whatnot. But fundamentally, if you want to formulate this again as a segmentation problem and you have like static images, then you can do that.
Like, I think CBT and Cornell's data set was trained on outdoor environments. Touchdown.
But touchdown was not predicting maps. Right?
Maps, yes.
No.
That's right.
Yeah. And they were doing this in static images.
Yeah.
Any other questions?
I got one. I didn't know anything about the semantic mapping, but I'm just curious. In the video, it seems if the robot is inside of bedroom, for example, how could it predict the semantic map like outside the bed?
Well, it's really struggling to do that. So what is usually able to predict is it is actually able to predict relatively accurately the free space outside the door. So it's able to predict like, a corridor and everything. But being able to actually, so as you can see here, like the agent is standing like in the corridor. So it's able to predict, that there is some corridor here and then there's another room here probably. It just predicts the layout there. But it's really very difficult to learn to predict, complete spaces, right? There's this, imagine like how big the space is here that you're trying to learn, especially when you're trying to learn associations that are between objects that are far away from each other. Like think of the space of possibilities that you have there. When things are next to each other, it's much easier to do so.
So, like in the training set, it will include some information like what could possibly be the layout or set the vector.
Yeah, so generally we use the ground truth, right? So imagine that for this prediction here, we would have this particular ground truth, right? But again, the model is maybe with more data, with more training, maybe we would be able to actually do that as well. But also notice that these scenes are like scenes that have not been observed before. So the model trains on 50 to 60 different scenes, and then tests on 10 to 11 other scenes that have not observed during training.
I have one last question.
Yeah.
So I noticed on like the numbers, like the success numbers, that they're actually kind of higher than what we were seeing on the semantic navigation problem. Look, yeah, and like you said, incorporating natural language helps like the maps be predicted better.
You're wondering why?
Well, well, so I mean, I guess like it could make sense. Like there are justifications. I don't know exactly why, but you have more information. So theoretically, you can predict more with more information. But my question was like, in terms of the formulation of this problem, like in these navigation problems, do you think that people should be working on the semantic navigation problem if like the ultimate goal is to navigate with natural language instructions? Do you think it's valuable to just try and navigate to semantic targets if like we can do better if we incorporate natural language, which is a more applicable end task anyway?
So first of all, I will answer both questions. So first of all, the criterion for success here is not as strict as in the object goal.
Oh,
So in the object goal, you have to be within 1 meter of the object. Here, I think it's 2 or even 3 meters.
Oh, okay.
Like if you declare to stop and we are within like 2 or 3 meters, I don't remember exactly, then you're considered successful. And that's how everybody evaluates. So I think that also obviously matters if you use the same. But this is, I think this is a harder problem because you have a more specific goal, right? For the object goal, you can navigate to any instance of the semantic target, and that will be considered successful. And the other thing is that I think it is valid to also investigate both problems, right? Because it's not exactly that one is a subset of the other. It doesn't mean that one is subset of the other, right? You can definitely there is definitely some overlap here, but there are a lot of use cases where you don't really need to give detailed instructions to a robot.
You can say, go find a chair.
To do something. Yeah,
And bring it to me.
yeah, exactly. And you don't necessarily need to, because these, if you notice, like a lot of these instructions are very detailed, and they're they're like defined in like egocentric space. So they're always written in the sense that you're the agent and you're kind of following that instruction. And so I think it's a very different problem in terms of that. They're not exactly subsets of each other. Anybody else have a question? Yes.
So for that particular question about segmentation navigation and this natural language navigation, I guess the one that might help one to be complementary to another one is that in a real world scenario, if you're given an instruction to the agent, that might not be 100% correct. The instruction might not be 100% correct. So is that possible that we incorporate the semantic segmentation and trying to like figure out what is wrong in the instruction?
Well, how do you know that the instruction is wrong? Because the same instruction can be, like if I ask five different people to actually write an instruction for this particular path, I'm going to get 5 different answers. Right? So how do you evaluate that that one is correct or not? You know, that is very ambiguous. Or like there is a very diverse way of solving these instructions.
There's a contradiction in the environment. Like go left, you're gonna see like the bed. There's no bed there. Then you could say there is a like mismatch between the instructions. But I don't think
we've actually seen a few cases where I think Karan, you also seen a few cases where the instruction might say, you know, turn towards your left to exit the door, but the door is actually like on the right. I mean, you can technically turn left all the way, like on the other side as well, but
it's not the instruction.
Yeah, but you see there are these small kind of inaccuracies here and there, but they're not like really big issue because you need to be able to address this variability in the language.
But you're also trying to like study these instructions. Something I noticed was that the instructions are very convoluted. They tend to put in a lot of redundant stuff. You see a beautiful painting and there's a man inside the painting and there's a hat on top of his head. This is like, so yeah, there's scope of improvement for sure.
I have one.
Yes, go ahead.
But I don't know if there is an answer to that. So I've seen like many papers in task and motion planning where typically the task is expressed like an LTL formula, and then there's a symbolic controller that gives you the actions. So I was wondering if you ever seen any paper dealing with taking the text, the human text, to get it transformed automatically to an LTL formula, and then execute what you're executing, like in the semantic navigation. Is there any paper like doing that? And if there is, do you think that they would perform that good as you do right now?
I don't remember a paper on the top of my head that does that. At least not in this literature that we have here. So this is at least the way that this task is defined is relatively recent. This is like started in 2019 or so. But there is a lot of prior work on language and navigation that was focusing in less realistic environments or completely in simulation. There is a lot using drones as well. I've seen a few papers before this particular task, spanning from like 2016 to 2018. And I don't remember anybody doing something like that. Everybody were just trying to learn some embedding from the language and then concatenate it with the vision and just try to predict an action. Right? They weren't really trying to do something as complicated as what you're saying. And I honestly don't know if it's going to work better. You know, that the details on the definition of the problem actually make a difference. Right? Here we operate in continuous environments, but the actions are predefined. Like the moving forward is 25 centimeters, turning left is 30 degrees or 15 degrees or whatever. So probably if you are able to actually predict how far you want to go every time or how much you want to turn, you know, kind of make it more realistic, then maybe what you're suggesting is actually going to be better.